So my name is Tristan Davey. I'm a senior software engineer with a company called RANlytics. The basics of RANlytics are we build cellular analytics hardware and software for cellular providers, governments, and other organizations that want to measure their cellular and RF environment. Tonight, I'm going to be talking about Unicode, and this talk is called Unicoding. It's about how to deal with Unicode encoded strings in programming languages in intelligent ways. Hopefully it won't be too boring. We'll see. I can't make any guarantees. So, what is Unicode? So Unicode is a set of character encodings that aim to encompass every writing system used on the planet. And I use the phrase writing system because it's not about encoding languages, it's about encoding the scripts that people write their languages in. And there's a lot of cases where multiple languages use the same script. For example, Farsi and different Arabic languages use the Arabic script. And a lot of European languages use Latin or Latin-derived alphabets. A character encoding is the piece that tells a computer that an A, or in this case a Latin capital A, looks like this in binary, or this on a signal on a bus or over the internet. And it's basically matching this sequence of binary here to the character itself. Most character encodings nowadays, like Unicode, also include things like helpful descriptions that tell you kind of what that actually is, as well as some additional information about how to form it that's kind of a bit more complex to go through. But whatever character encoding you're talking about, everything that you do on a computer is encoded in one way or another, whether it's programming, sending messages, sharing memes, printing. There is always something that is using a character encoding there to encode all of that text. And the most important thing about character encodings is they let people express themselves. They let them write their name. They let them say the things that they want to be able to say on a computer. If you talk to someone who has a name that's non-Latinized, or even is Latinized in an unusual way that's not within the standard ASCII character set, they'll often tell you about the frustration of having to write their name in online forms, in computer programs, and not understanding how that's actually going to be treated. Some of you in the room may know Gonzalo. He had a constant frustration. He's a software engineer I used to work with, and he had a constant frustration that he never knew when he entered his name whether this C was going to be printed, it would come out correctly, or whether he'd just get a rectangle on a form somewhere. So Unicode came about in the early 90s. It was in response to a couple of standards developed in the late 80s that didn't really fulfill the need to represent every character on the planet. Unicode 1.1, which tells you a lot because they didn't even get to release 1, it already got to 1.1, was a single encoding, included 23 scripts, primarily European and Middle Eastern scripts, and encoded 7,163 characters with space for up to 65,000. At the same time, a group of software engineers, part of the Unicode consortium that developed Unicode, were working on developing a system to encode Han characters. That is the traditional Chinese, Japanese kanji set, as well as traditional Korean set. They counted to about 40,000 of those before they realized that they probably weren't going to be able to fit it into the 65,000 that they'd allocated. And so Unicode evolved. And in 2021, we're up to Unicode 13. It has 3 different encodings, encodes 154 scripts, both current and historical. 140,000 characters are already encoded in it, with about 1.1 million points available to encode characters in total. So, we're a little over 10% there to filling up the entire encoding. Most importantly, most of you are aware that Unicode gives us Emoji. They're the organization that controls Emoji. They decide what goes in, and they tell computers how to encode it and send it to other people. We're going to have a quick look at the basics of Unicode so you get a bit of an understanding of what Unicode involves. These are individual characters. The Latin character A, the pile of poo emoji, or the helpfully named CJK Unified Ideograph 653F. Each of these characters has a set of properties, and that is kind of how it's presented, how it looks, a description of what it is, an index, which is basically, as you'd expect, an index from 0 to however many characters there are of where this sits within the standard. And then every character has a couple of hex and binary or bit representations. And those binary and bit representations are the encodings of them. Here, this is the basic Utf-8 encoding, which coincidentally is backwards compatible with ASCII, if any of you learnt ASCII in university or school. And we'll have a look at a bit more detail of the three main encoding schemes. Now, there's actually kind of about 6 or 8 of them, depending on what you want. But most of them are based off these three schemes, and by far Utf-8 is the most common. On the internet, Utf-8 makes up 97% of all internet traffic, and there is almost nothing in Utf-16 or Utf-32. Utf-16 is actually used in a number of programming languages as a native string encoding, but otherwise isn't used for transmission because it's not particularly efficient. Utf-32, basically not used for any transmission at all, but it is used in a lot of legacy computer systems. So if you're running mainframes from the 1970s and 1980s, you can use Utf-32 to encode modern strings into those systems because they're a fixed length, they're always 32 bits, so you know how long any character is going to be. But the other ones have variable lengths, so any Utf-8 character can be between 8 or 32 bits, any Utf-16 character between 16 and 32 bits. There's also some properties about them, how their endianness is. Utf-8 has no endian properties. It's always oriented the same way, but Utf-16 and Utf-32 both are big and little endian. We'll walk into that a little bit further later. And this is a quick look at kind of how characters look in each encoding. So this is Utf-32. I've got hex encodings to represent each bit or each byte in the actual encoding on disk or in memory. And it's pretty simple. Index 41 corresponds to a 0-padded 41 binary representation, 653F, 653F. Pretty simple to understand. Utf-16 gets a bit more complex because the first 65,000 characters conveniently fit into 16 bits or 2 bytes. So they're all kind of how you'd expect, 65-3F, 65-3F. But larger characters that don't fit in the first 65,000 get encoded slightly differently, and they end up at 4 bytes. Again, we'll look into that a little bit more later. But really, Utf-8 is where it's at. Most of us, day to day, are dealing with Utf-8 encoded strings. It's the native encoding of Linux and Mac OS. Windows has had native support for it for 20 years, and pretty much every application on the internet or you run on a PC or Linux box nowadays encodes its strings in Utf-8 when it writes them to disk or puts them into memory. Utf-8 is variable length, so it's the most efficient way to represent things, but it's not necessarily the easiest thing to understand. And you'll see here that the basic Latin character A has a very basic representation. The first 128 characters actually match up to their ASCII representations for backwards compatibility. But once you get outside ASCII, things go a little bit crazy. You'll see here that even though this Russian character here is 041F, its representation is DO9F. And the reason for that is the way it's encoded in the binary. It doesn't necessarily make sense on a byte by byte level, but if you look at the binary itself, it does. So Utf-8 is byte bounded with 6 bits per byte outside the first 128 characters. So you can see here the character at index 41 is encoded as 41 in binary, but this character here is actually encoded in this way where the first byte, or the most significant byte, 1F, is encoded in the red bits here as 6 bits in the last one, and then 2 bits in the first one, and then the 04 is represented in 3 bits in the first one. Now, that gets a bit more complex, or you probably don't need to deal with it all really. If you do need to deal with it, it will be very rarely. One thing to know is that these bits at the start are particularly useful. And that's probably the main time you're going to deal with them if you're intercepting, say, a USB stream or something like that where you're expecting UTF-8 characters, you can use these to indicate the start of a character. So you can see that any character that starts with a 0 is always going to be a single byte character. Any character that starts with 110 will be a 2-byte character. Any character that starts with 1110, 3-byte, etc. And then all the subsequent bytes start with 10. And so you know that if you stumble into a stream and you start reading characters and bytes out and you see a 10 at the start of a byte, you probably know I'm in the middle of a character. I need to ignore that until I see something else. Now we talked about endianness. UTF-16, UTF-32 have both little endian and big endian representations. And the way to tell them apart is every UTF-16 or UTF-32 string will be prepended with a byte order mark, which is just a character that tells you what order the bytes are in. It's pretty easy. And it's formatted in a particular way, FE, FF, or this binary representation here, which means that when it's little endian, you'll see it one way. When it's big endian, you'll see it the other way, which is a pretty useful thing. And it's always right at the start of the string. So you can read in the first byte and understand what am I reading next, and in what order am I reading it in. So like what is this, a 2002 hit, Missy Elliott song, Work It. When you see one of those, you have to, I've got to read it, put it down, flip it and reverse it. So basically that just means when you see FF, FE, you're in little endian orientation. When you see FE, FF, or the binary representation of that at the start of a string, you're in big endian. What does that mean? If you're not familiar with those terms, it just means that the bytes are in different orders. So this is UTF-16. You're looking at 16-byte characters, 16-bit characters, 2-byte characters. And so in little endian, your least significant digit is first. In big endian, your most significant digit is first. Very simple. In UTF-32, it's the same, but just with 4 bytes rather than 2 that are reversed. Again, most applications will handle this for you, but it's very useful to understand when you're dealing with streams, in particular on the internet, from some of the more modern socket technologies. Now we get into the complex bit. So it's all nice and good to be like, oh, I don't have to deal with that low-level stuff. But there's one thing that we all do a lot of, and that's restricting what users can input in forms, truncating what they put in forms, and dealing with user-inputted strings. And one of the things we do is we look at string length a lot. So we're going to have a pop quiz. There's this character here. This is C. It's encoded in UTF-8. What is the string length of this single character string? 3? Oh, you got it. So it's 3 because it's a 3-byte character, right? And so older languages, or even modern languages that work on a byte-by-byte level, will treat string length based on byte length because they're expecting single byte characters as per kind of the old days when ASCII was how strings were represented. The one thing you have to be careful of is new languages don't conform to this. So Python 3, for example, is Unicode aware. If you ask for the length of a string in Python 3 that has Unicode characters, it gives you the number of characters, which is kind of what you expect. But when you're switching between them, you have to remember which one's which, otherwise you're going to get yourself into trouble. Another problem is hidden characters, characters that are kind of there but hiding in plain sight. So there's lots of these. I think there's probably a couple of hundred in total across the Unicode standard. The most common ones you'll see, null. If you've worked with C before, you'll know that null-terminated strings are quite common. The particularly fun alert character, which if you're working on a 1960s teletype will ding the bell. If you're working in a modern terminal, just makes a noise. Or things like the zero-width joiner, which is just a character that has no width and doesn't join things. We'll look at why that's important. Because there's this string here, right? I'm not going to try and say this. It's a German word. I don't know German. but it means addition in German. And it's a conjoined word, 2 words joined together. And you'll notice that the string length of this, even in Python 3, is 8. And that's because there's a hidden character in it. You can't see it, and that's because it's that zero width non-joiner we were talking about. And why it's important is, if you remove it, something happens to this word. Sorry, that's what it looks like. So there's a hidden character in there, which if you escaped it would look kind of like this. If you remove it, these 2 characters get joined together. And that's because German has a ligature between the F and L characters. If they're a single word, they get joined together into a ligature, has a completely different meaning. When it's a conjoined word or 2 words put together, those ligatures shouldn't join. The computer doesn't know the difference, so it just always assumes that those ligatures are going to join. Unless you tell it, it's not going to. And that's what the zero width non-joiner is for. It's to tell the computer, don't be stupid, don't join these things together. And you'll see these all the time in other languages because they're necessary for the computer to work correctly, because we built computers to work with English, and they still don't really work that well with other languages even now. We're going to look at a slightly different case now. And this is the Brahmi letter nya, 3-byte character. If we look at it in UTF-16 though, it's going to overflow that 16-bit representation, and it's going to split itself in half. So if we looked at it in UTF-32, this is what it would look like, pretty straightforward. When we look at it in UTF-16, it's this representation here. And what it actually is it composes it of 2 characters. And these are called a surrogate pair. And basically, if you're anywhere from that 64,000 to the 1.1 million characters, and it's represented in UTF-16, it ends up being 2 characters when it's stored to disk or in memory. Now, you may be like, why is that important? Well, it actually affects string length, unfortunately. So when you're working with UTF-16 encoded languages, for example, the very popular language JavaScript, it will compose characters like this of 2 separate characters and count them as 2 separate characters. So the surrogate pairs work by basically creating a matrix of 1,024 high surrogates, 1,024 low surrogates. You pair each of those up in a unique combination and you get one of the code points from 65,000 to 1.1 million. It's kind of an odd way to do it, but it's a workaround for the fact that no one thought about this when they designed the encoding. But yeah, if you look at it in languages like JavaScript, and that even means if you pass in a UTF-8 string into JavaScript in a browser, in Node.js, it transforms it to UTF-16, and this character will always be 2 characters long, no matter what you do about it. And everyone's brain is exploding right now because you're like, do I even trust what string lengths are telling me anymore? We'll get to that a bit later. Because there's more. There's combining marks. And these are another problem. Because combining marks work by combining 2 characters to make 1. Pretty simple. Here, if we wanted to write the small Latin U with the diaeresis, you write U with the diaeresis combining mark, which is another Unicode character. And Unicode understands to combine these into 1 character. Looks like 1 character is equal to 2, even in Python 3, Python 2, no matter what you look at it in. So what if I asked you, how long is this character? And you all know this is a trick, so is anyone going to tell me? David? Python 2 or 3? It's any Python version, actually. No? Okay. So it's 1. And that's because there's 2 representations of this character in the most confusing way possible. So you can either construct it by combining 2 characters, the U and the combining mark, or by using that character's own index. We'll talk about how to avoid this later, yeah? Why? Okay, I can actually answer why. So the reason is that a lot of common Latin characters were encoded on their own. So someone decided that this character is used often enough in a number of different languages, primarily Nordic, I believe, that it deserves its own code point. But they're also determined to make it easy to compose a lot of those characters with other pieces if you didn't have a keyboard or another input device that could just type that single character. So they made this combining mark scheme so that you can either construct really complex combining mark combinations. You can actually kind of just add 20 combining marks to a single character even though it doesn't make sense. Or if you wanted to just take a standard Latin keyboard, type a normal U, and then press a keyboard combination to put in the combining mark to make it the U with a diaresis.
So another way, the option on the left is more so that the symbols, the diaresis can be used with other symbols as well.
That's right, that's right.
Whereas this is a symbol.
Yeah.
It's almost like backwards compatibility of sorts. It's kind of, it was there, so we'll just keep one on.
Yeah, it is built for compatibility, and also because, yeah, as you said, diaresis can be combined with any character in reality. It may not necessarily make sense, but the combining marks are built so that that can happen, even for characters that may only exist in one language and don't deserve their own code point. I say don't deserve, they probably all do, but decisions had to be made. So you'll see a lot of characters that look the same, but aren't quite the same underneath. So this is the individual representation with the two separate characters. It has a length of 2. The combined one has a length of 1. Very easy to understand, right? There are some solutions to this, and it's graphemes, which you can remember by thinking of graph memes, but not graph memes because there's no M in the middle. And so graphemes are this concept in Unicode that describe what a character actually is. And that is the boundaries of a represented character in print or on a screen. And so what we have here is a grapheme, which is a ligature of 2 Arabic characters. There's a lot of ligatures in Arabic because it's traditionally a handwritten language before computers. And so a grapheme says, this here is a single character, even though it's composed of 2 different code points. Now, if you went through any language, it would tell you it's 2 different characters, but you can use Unicode's grapheme functionality to help you find out more about the actual length that's printed of characters that's printed on the screen. And this is because there are some quite complex characters in Unicode. This is a Devanagari character that's composed of 4 different characters combined. And you can see that kind of some of these elements get carried over into it, but it's a unique character on its own. It's not actually characters joined. And the reason this exists is because Devanagari has hundreds of these different possible combinations. And so the best way to encode it is by combining separate characters that actually compose into these complex graphemes. Another example of this is emoji, and we'll use the emoji because they're a pretty simple concept to understand. So the flag emojis are actually made up of 2 characters underneath. They're special characters built for the flag emojis called regional indicators. And for example, the flag of Estonia is made up of 2 of the same character, the regional indicator symbol E, catchy name. But if you put 2 of these together, Unicode knows that's the Estonian flag. Great. Python 2.7, however, will tell you it's 8 bytes. But you can kind of fix that. By the way, Python 2 says that's 2 characters still. Sorry, Python 3 says that's 2 characters still. You can fix that with using graphemes. So this is a Python 2.7 library, but Python 3 libraries exist, and libraries exist for most languages that have the ability to recognize graphemes. So they understand what in the standard says is a single character when combined, and can go through a string and count those for you. So the Graphemes library in Python 2.7 knows that this character, even though it's composed of 2 different characters inside, is a single grapheme. And most languages have the intelligence to be able to do this with a library now. There are still some limitations on this because it's a kind of complex pattern matching problem, but you should be able to find for any modern language you're using, there's a grapheme splitting or a grapheme recognition library that can count those individual symbols in a string more so than the individual characters or the bytes. And this brings us on to the topic of string equality, because we spoke about that character before, the U with the diaresis that has two kind of permutations, and we'll look at that again. To the untrained eye, or really anyone who is logical. These look the same, right? You want the computer to actually tell you they're the same thing. That's really what you want. If someone puts their name in, you want to be able to match it against another record by someone that put the same name in. You don't care about how the individual characters were encoded. So you can do that in some ways. Sorry, this is just an example to say they don't match. If you compare them in pretty much any standard equality, languages do bitwise comparisons for these types of things. Doesn't work. The way to fix this is through transforms. So Unicode has built in a set of transforms that know the simplest and most complex forms of any character. That means that you can take the complex form of this, which is made up of 2 characters, transform it into the single one. And there's standard libraries for this across a pile of things. I'm using Python as the example. This works on Python 2 and Python 3. But using the Unicode data library's normalize function, I can take this character here with the 2-byte representation and turn it into the single byte representation by running it through this function with a set of flags. And those flags basically tell it, please normalize this for me and get it to the simplest form. You can go the other way. You can denormalize with another set of flags, NFD. And you can even do this with like other weird characters. So Unicode has all of these characters that are Latin characters in circles. I don't know why, they're just there. But you can ask it to give you a nice, simplified character. And it works for all of those kinds of special characters where it has a simplified representation or a denormalized representation. For example, the trademark sign can actually be put in and be simplified down to T and M as it comes out. If we're looking at a string of flags, emoji flags, we can have a look at kind of something like this, where we're looking for the Swedish flag inside a string which is made up of the Spanish and Estonian flags. And you may be like, Tristan, that's not going to match because the Swedish flag isn't in there. But you're wrong, because it does, because it matches the individual bytes bit by bit. So the Swedish flag is composed of 2 characters, 1F, 1F8, and 1F, 1EA, which just happen to be the last byte of the Spanish flag and the first byte of the Estonian flag. So even though you're like, I want to match this character inside here, if you're doing any simple comparisons in really any programming language, except for ones that are very Unicode aware, it's going to tell you it's actually there. And that's not the programming language's problem. It's just kind of like working within the parameters it's given. It's looking bit by bit and just kind of understanding what's happening. Again, Graphemes save the day. And because each of these is an individual grapheme, we can use something like the Grapheme Library to solve this problem. Here in Python 2.7, grapheme.contains can do a simple comparison to look for an exact match of graphemes inside a string. String slicing and truncation. Again, this is something that we do from time to time. You may be outputting data on a screen and you need it to be shorter in case it's too long. You may be putting things into data fields in a database where it has a fixed length. There are a couple of problems with that, and that's a blank slide. So we're going to jump back to that Brahmi letter before. Again, 3-byte character. Looks like that. We all know that. If you look at that in JavaScript and slice it in half, you get a broken character. And that's because JavaScript is just doing basic byte-by-byte comparison. If you take a substring of it, it's going to give you the first character without the second. In this case, it's a surrogate pair, so the first character means absolutely nothing. And so it will give you this character here, which is a Unicode replacement character. And this happens in a number of different situations. JavaScript is particularly a problem because you're dealing with a lot of unknown inputs and things like that that you don't know necessarily what's put in, and it's transformed to UTF-16 for you, and you can do substring and matching on that and slice things in unusual ways. But it can also happen in examples where, like in Python 2.7, if you were to take the first 12 characters of this string here, you end up breaking the second flag and leaving some broken data in the string, which if you output it in a UI is going to give you this kind of broken character icon. Again, Grapheme save the day. You can use something like a Grapheme slice to slice that down. Again, this is pretty common in most of the Grapheme libraries that it's a feature. In this case here, what it does is it searches forward. So if we give it an end of 12 bytes, it searches forward, goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then at 12 goes, there's no Grapheme boundary here. This is not the end of a Grapheme. And then searches backwards to the end of the last symbol or Grapheme. Now, that's most of the string handling done. Excuse me. The other problem that we often run into with Unicode is sorting. We're all used to putting out lists in UIs or getting data out of databases. And most of us just think, well, we can just rely on the database to sort that for us, or whatever the default sorting the language does for us is. That's fine in certain cases, but there's a couple of problems with like magically trusting that sorting is happening in the right way. And that's it. It might look right to you, but it may not be right for every case. So, most commonly, languages do a bitwise collation sort, right? That is, they're looking for the bit representation and they order in order of the bit representation. In this case, the index is the bit representation for most of these characters, so they're ordered in that way. Unicode does offer a default collation sort, which is just kind of like a way that they suggest you sort things if you don't know how to sort it. That obviously has some differences to bitwise. It can do really nice things, like it knows that the A's go together, for example. But otherwise, if you're using this bitwise collation, you'd end up with some of the A's with accents after your entire, kind of standard Latin alphabet. But where this really comes to shine is if you know the user's locale. So if you're working on a computer that has a system API that can give you the language they're working in, if you're working in a browser that can tell you the language that the browser is set to, you can customize this immensely. And that becomes very useful for, in particular, Latin languages, but also languages that have completely different sorting methods for even Latin characters. So on the left here, we have the US English collation sort. That's pretty much how you would expect. One thing to note here is that this character here, 00C6, it's what we call in English the Ash ligature. Fell out of use in the 18th, 19th century in English. We still have it in words like encyclopedia sometimes. It's still an actively used word, or character rather, in the Icelandic language. And so in Icelandic, it's in a different position. It's actually in the kind of GE range. And so whilst in English, we'd traditionally sort it back here, in Icelandic, it's useful for users in that language to take the same strings that they'd be looking at and have that character sorted further down in the alphabet. And if all this is starting to sound too hard, I've got good news. There's a very simple way to do this. Most languages nowadays have a standard library or a set of libraries provided by Unicode that can do a lot of these types of things. In this case here in JavaScript, the INTL library gives you custom collators based on a locale string. If you're doing this in a browser, you can grab that from a browser API and just pass it in, and it will do everything magically for you. But these form part of a standard called two sets, the International Components for Unicode and the Unicode Common Locale Data Repository. And these are Unicode provided libraries for programming languages that help you do a lot of these internationalization tasks around how to handle characters in different contexts. They're not going to help you with that string counting, string splitting problem, but they'll help you with things like sorting. So the ICU is published in C and Java and ported to nearly every language on the planet. The CLDR, or the Common Locale Data Repository, is a set of kind of interchangeable data formats that just tell you for Icelandic, sort in this way. And those are also built into a lot of libraries on different systems. Here we've just got a selection to show you that kind of everything from the most modern languages like Go, Lang, and Clojure have options to JavaScript, Java, C++, etc. In a lot of cases, these are built into the standard library nowadays. The last thing to consider with Unicode, which is more of a kind of last minute consideration because it's built into kind of UI coding and things like that, is what's called tofu. And I kind of referenced this earlier, and it's those unprintable square rectangles that you get sometimes. They're not too common nowadays because computer support for different languages has gotten a lot better, but anyone who was around on the internet in the early 2000s will probably remember these being very prevalent. And it was just basically rectangles everywhere if you went outside your supported language. So here's an example, and up the top we have an Armenian poem, and down the bottom we have the same Armenian poem, but can you notice a difference? And that is, the top one is in a font called Noto Font, which just happens to support the Armenian character set, and I say just happens to, it deliberately supports it. The one at the bottom is a standard font that doesn't support Armenian. It's very simple. So when you're looking at programming your UIs, it's important to consider the fonts that you're forcing on users and whether that's going to support the languages that they're inputting data in and whether there's a logical fallback for that. So in browsers, actually, a lot of them will default fallback to system fonts that it understands have different characters without your consent. You can't do anything about that, but it's good for user experience. When you're making PDFs or building UI applications, though, that isn't the case. And it's up to you to make sure that you've got the right fonts referenced for your application to be able to reproduce characters effectively. And this is particularly a problem for Chinese, Japanese, Korean, and to a certain extent, older Vietnamese speakers, because they have huge character sets that almost aren't included in any default font. In Chinese, Japanese, Korean, which is the Han set, there's upwards of 60,000 characters. Some of those aren't used that often, but there's about 40,000 that are used commonly. And the simple fact is that they don't get bundled into operating systems that commonly because they're huge, right? That's just how it is. If you need to support different things, there's some options out there. Google publishes the Noto Font, which is a large font repository, 17 fonts, different styles, different boldness and thicknesses and italicized, totaling 1.1 gigabytes, but it supports 65,000 characters. You can cut that down if you just want a single kind of weight and style, but if you're just looking for that, something like the new Unifont might be a bit better. It's a combination of 5 different fonts that cover about 63,000 characters across a variety of different languages, all of the most commonly used. And it's only 25 megs. Windows users, if you've got Microsoft Office installed, Arial Unicode MS has come with most Microsoft Offices by default since 2003. Supports 38,000 characters out of the box. It's one of the few fonts that you'll find by default on operating systems that has wide support. And if you're dealing with the Asian market with Chinese, Japanese, Korean speakers, traditional Vietnamese speakers as well. Modern Vietnamese is written in Latin, but traditional Vietnamese was obviously a different script. There are options around that as well. So New Guilin is a font that largely supports most of the current and historical Han scripts. So it also includes Japanese katakana and a couple of other more modern scripts, Hangul, which is modern Korean. But it will basically allow anyone from the China, Japan, Korea region to be able to write in traditional or modern scripts. Han Nom is similar, but it's more comprehensive. The difference is it also has the Nom scripts, which is the traditional Vietnamese writing script as well. So if you're looking for options, you can embed these in your application. Some of these are available open source, some of them are shareware, some of them have other commercial licenses available. If you just want to add them to your fallback list, that's a good option as well. You'll in particular find that a lot of users in mainland China or Japan will have these fonts installed already, and you can just fall back to them by default. So if you're looking for resources, the first place to go is always the Unicode standard. I guarantee you don't want to go there all the time because it's in print, it's a kind of multi-thousand page document. But if you're looking to understand specific things that are happening in your strings when you see something odd, it's the place to go. It's very well organized and searchable. The other pieces we spoke about, which are the international components for Unicode, have a standard website that you can look up what your language's library is and how to use that. And the CLDR is also there. The CLDR is actively developed, so it gets updated about twice a year. You'll find that sometimes new things get introduced that you might need to pull in the real data from the Unicode consortium itself. I can also answer any questions you have, at least within my knowledge, and obviously these slides will kind of go up somewhere after this, and you can contact me and I can give you a link to that, or you can watch the YouTube video back. But the most common way to find out about these things is just to Google them. Someone else has almost certainly had a problem before in supporting a certain language or have seen a certain oddity in their script handling with Unicode characters. And they'll already have the answer for you on Stack Overflow or something like that. It's just a matter of thinking about the way that you're handling that data when you're handling it, and making sure that you're taking what you've learnt tonight into consideration to have a better experience for your users, in particular those that come from a non-English speaking background. That's it. If anyone has any questions, let me know. I know we've been going for a while, so otherwise, that's it. Thank you all. You can find me on Twitter if you like my rants, and GitHub if you like looking at outdated open source code.